Hello students, welcome to the EPG Pathshala. My name is Dr. Shashi Sharma. I am Assistant Professor in MIT Institute of Biotechnology at MIT University, Noida, UP. I am going to talk about the module Bioprocess Engineering. Bioprocess engineering is the discipline that puts biotechnology to work. It evolved from an interdisciplinary subject area of biology and chemical engineering and has matured to a discipline that intercepts chemical, mechanical, electrical, environmental, medical and industrial engineering fields. Bioprocess engineering thus encompasses the design, operation, control and optimization of biochemical processes involving various biological pathways or reactions mediated by living cells of animals, plants and microorganisms or enzymes under controlled conditions for the efficient biotransformation of raw material into a range of products at requisite scales. The product may be directly useful as food, medicine or the industrial compounds or indirectly in the way of bioprocess without any direct product formation as in the detoxification of industrial wastes or treatment of factory effluents. Bioprocess engineering is thus the backbone of the biotechnology industry that translates the research and development to the industries and is divided into three parts as per the processing. The first part is upstream processing, the second bioreactor and bioreactions, and the third is downstream processing. With this, the following objectives of this module are designed as to understand the fundamental basics of microbial kinetics, metabolic stoichiometry and energetics. Second, to understand the basics of bioreactor engineering with knowledge on design and operation of fermentation processes. And third, to develop bioengineering skills for the production and purification of biochemical product using integrated biochemical processes. Upstream processing. The upstream processing of a bioprocess is the initial step in which the microorganisms or cell lines are grown in bioreactors using the basic steps as inoculum preparation, media formulation, improvement of inoculum by genetic engineering, growth kinetics optimization with an aim to increase the production levels along with the regulation of temperature, pH and pressure. Starting with the inoculum development, inoculum production is a critical stage in any industrial fermentation process. Obviously, one loop of cell line requires a prolonged period if it is directly introduced into fermentation. Thus, inoculum is prepared as a stepwise sequence employing increasing volumes of media. The preparation of a population of microorganisms from a dormant stock culture to an active state of growth that is suitable for inoculation in the final production stage is called inoculum development. Inoculum for industrial fermentation should be in its active, healthy and exponential growth phase to reduce the lag phase. It should be available free of contamination in required large volumes. It should retain its capability for formation of desired product formation. Inoculum development is usually done in a stepwise sequence to increase the volume to the desired level. As a first step in inoculum development, inoculum is taken from a working stock culture to initiate growth in a suitable liquid medium. Bacterial vegetative cells and spores are suspended usually in sterile tap water which is then added to the broth. In case of non-sporulating fungi and actinomycetes, the hyphae are fragmented and then transferred to the broth. At each step, inoculum is used at 0.5 to 5% of the medium volume. This allows a 20 to 200 fold increase in inoculum volume at each step. Typically, the inoculum used for production stage is about 5% of the medium volume. Medium formulation. All microorganisms require elements as carbon, nitrogen, mineral, possibly vitamins, water and oxygen if aerobic for their sustenance. Hence, the formulation of the nutrients is the most important requisite for the optimized production of the desired product, cell biomass or a specific metabolite, and there must be an adequate supply of energy for biosynthesis and cell maintenance. This is well depicted in figure 1, which highlights on the substrate input and output of the cell. So, first strategy for a rational design of fermentation media is according to the elementary composition of a specific microorganism and of the main product that is produced. Second is to design according to the stoichiometry of growth and product formation, which is represented by the chemical equation as CWHXOYNZ, which is a substrate, plus A moles of oxygen plus B moles of nitrogen source HgOH results in the biomass production with C moles CH alpha O beta and delta plus D moles of carbon dioxide plus E moles of water plus F moles of product, that is CJHKOLNM. Microbial growth stoichiometry involves the conversion of substrates into products and cellular materials and helps to determine the true yield coefficient based on substrate for biomass, that is Yx over S, and for product, that is Yp over S. So, Yx over S is equal to quantity of cells produced in grams per quantity of substrate consumed, and this is equal to C moles of the molecular weight of cells upon the molecular weight of substrate. Similarly, Yp over S, that is the product yield, is equal to quantity of product produced divided by quantity of substrate consumed and is equal to F moles of the molecular weight of product divided by the molecular weight of substrate. Thus, complete knowledge of elemental composition of a specific industrial microorganism helps in the refinement of media formulation. Criteria for selection of a media is thus maximum product or biomass yield per gram substrate consumed, maximum purity of product or biomass, maximum product formation rate, low unwanted product yield, cheap, consistent quality and availability throughout the year, and minimal troubleshoots in upstream and downstream processings. The composition of a fermentation media may be simple to complex depending on the particular microorganism and its fermentation. Autotrophic microorganisms require only the simplest of inorganic media like inorganic salts, water, nitrogen source, carbon source is fulfilled by carbon dioxide or bicarbonates and are capable of synthesizing all the complex organic compounds required to sustain life. Fastidious microorganisms, on the other hand, lack the ability to synthesize many of their sustenance and growth requirements. Hence, they require the presence of many simple to complex nutrients in the medium and must have an organic carbon supply to provide for synthesis of cell substances and release of metabolic energy. Thus, simple and complex media are further characterized as synthetic and crude respectively. Synthetic media comprises of the components which are specifically defined and are known compounds. Each component is relatively pure and the exact concentrations are known. Concentration of one or several can be varied to determine the effect on cell growth and product yield, and individual components may be deleted or added as well. However, these are expensive due to the relatively pure ingredients used and yields derived from these media are relatively low. Coming to the crude media, such type of media usually allows much higher yields. They contain crude or undefined sources of nutrients and growth factors. To make the process cost effective, industrial scale fermentations primarily focuses on the use of complex crude substrates mostly derived from natural sources as plants or animals, industrial byproducts where many carbon and nitrogen sources are almost defined. Water is the major component of all fermentation media and is needed in many of the ancillary services. Energy sources. Energy for growth comes from either the oxidation of medium components or from light. Most industrial microorganisms are chemoorganotrophs. Therefore, the commonest source of energy will be the carbon source such as carbohydrates, lipids and proteins. Some microorganisms can also use methane or methanol as carbon and energy sources. Carbon sources. Carbohydrates constitute the most predominant source of energy in fermentation industry. Refined and pure carbohydrates such as glucose or sucrose are rarely used for economic reasons. Hence, the industrial byproducts which serve as carbon sources are preferred. Molasses. Molasses is a byproduct of sugar industry and is one of the cheapest sources of carbohydrates. Sugarcane molasses, which contains sucrose around 48%, and sugar beet molasses, which contains sucrose about 33%, are commonly used. Besides being rich in sugar, molasses also contain nitrogenous substances, vitamins and trace elements. Hydrol molasses, which is a byproduct in glucose production from corn, is also used as a fermentation substrate. Malt extract. An aqueous extract of malted barley contains about 80% carbohydrates containing glucose, fructose, sucrose and maltose. Nitrogen compounds constitute around 4.5% with proteins, peptides, amino acids, purines and pyrimidines. Starch, dextrin and cellulose. Due to their wide availability and low cost, the polysaccharides starch, dextrin and cellulose are frequently used for the industrial production of any metabolite. Whey. Whey is a byproduct of dairy industry and is produced worldwide. It is reasonably good source of carbon for the production of alcohol, single cell protein, vitamin B12, lactic acid and gibberellic acid. Methanol and ethanol. Some of the microorganisms are capable of utilizing methanol or ethanol as carbon source. Methanol is the cheapest substrate for fermentation, however it can be utilized by only a few bacteria and yeasts. Methanol is commonly used for the production of single cell protein. Ethanol is rather expensive. Now the substrates which can be used as nitrogen sources. The nitrogen supply to the fermentation microbes may come from inorganic or organic sources. Inorganic nitrogen sources comprises of ammonium salts and free ammonia, which are cheap inorganic nitrogen sources and are easily utilized by some microbes. Organic nitrogen sources. Urea is fairly a good source of nitrogen. Other cheaper organic forms of nitrogen are also preferred as corn steep liquor CSL, which is formed during starch production from corn. It is rich in nitrogen, about 4% of nitrogen is present, and in several amino acids as alanine, valine, methionine, arginine, threonine, glutamate, and is very efficiently utilized by microorganisms. Yeast extracts contains about 8% nitrogen. Yeast extracts contains about 8% nitrogen and are rich in amino acids, peptides and vitamins and are very good sources for many industrially important microorganisms. Soy meal is the left out residue after extracting the soybean oil from the soybean seeds. It is rich in proteins, about 50% of protein, as well as carbohydrates, about 30% content. Peptones. The protein hydrolysates are collectively referred to as peptones and these are good sources for many microorganisms. The proteins namely casein, gelatin and keratin can be hydrolyzed to yield peptones. Peptones are relatively more expensive, hence not widely used in industries. Growth factors. Some of the microorganisms are not capable of synthesizing one or more growth factors such as vitamins. These growth factors are very expensive in pure form, hence crude sources are preferred. Yeast extract is a rich source of almost all growth factors. Criteria for selection of raw materials include: first is it should be inexpensive, consistent quality and easy availability. Second, ease of transport in any form. Third, should withstand sterilization procedures. Fourth, favorable properties that may influence agitation, aeration and foaming. Fifth, increased levels of desired product with respect to its production rate and yield per gram of substrate. Sixth, low quantities of impurities. And seventh, overall health and safety implications. For the media, buffers are also used which maintain the pH. In the media, some precursors, inducers or inhibitors are also added during the course of fermentation for the targeted production of desired products. For example, phenylacetic acid is added as a precursor in the production of penicillin G. In most cases, inhibitors are effective in increasing the yield of the desired products and in reducing the yield of undesired related products. For example, sodium bisulfite acts as inhibitor in glycerol fermentations. Certain inducers are also added in medium to induce enzyme synthesis or activation. For example, beta-galactosidase in E. coli is induced by the presence of lactose or with molecules having similar structure to lactose. So, media formulations and environmental conditions drastically affect the physiology, biochemistry and the morphological changes which further influence product yield and other fermentation properties. Coming to the oxygen requirements, it is sometimes forgotten that oxygen, although not as such added to a medium, is nevertheless a very important component of the media in aerobic processes, and its availability can be extremely important in controlling growth rate and metabolite production. The medium may influence the oxygen availability in a number of ways. Fast metabolism, if rapidly metabolized substrates are present in high concentration. Rheology, the individual component of the media can influence the viscosity of the final media and its subsequent behavior with respect to aeration and agitation. Antifoam, many of these act as surface active agents and reduce the oxygen transfer rate. So, in the cultivation media table, we can see the various sources and the defined components and the undefined components as I have discussed earlier. Animal cell culture media. Animal cell culture media are normally based on complex media such as eagle cell culture medium containing glucose, mineral salts, vitamins and amino acids. Mammalian cell medium usually contains serum as rich source of essential growth factors including initiation and attachment factors and binding proteins, supply hormones, trace elements and protease inhibitors. Plant cell culture media are usually chemically defined. They contain an organic carbon source, a nitrogen source, mineral salts and growth hormones. Sucrose is frequently incorporated as a carbon source, particularly for secondary metabolite production. Nitrate is the usual nitrogen source, often supplemented with ammonium salts. However, some species may require organic nitrogen, normally in the form of amino acids. So, after studying about the various parameters which influence the growth of the microorganism, let us now concentrate on the microbial growth kinetics and specific growth rate. Now, growth of microbes is an autocatalytic process, that is, the growth rate is proportional to the biomass. Thus, microbial growth can be described as a proportionate increase in all its cellular contents in the presence of appropriate medium and the culture conditions. Mathematically, it is expressed as dx upon dt is equal to mu x. where x is the concentration of microbial mass, t is the time in hours, and mu is the specific growth rate per hour. Now integrating between time t0 and time t, when the concentration of cells are x0 and xt, we get the equation xt is equal to x0 e to the power of mu t, where x0 is the original biomass concentration, xt is the biomass concentration after a time interval t hours, and e is natural logarithmic base. Now taking the natural logarithm, we come to a final equation log xt is equal to log x0 plus mu upon 2.303 into t. Thus a plot of log xt versus time t results in a straight line with slope equal to mu upon 2.303. Bacteria divides by binary fission, and the increase in bacterial population density is given by geometric progression. The time required to double its number is known as generation time and is given by the expression let Td be time taken for an initial cell population N0 to double, that is N is equal to 2N0. So substituting the values of N and T in equation 5, we get natural logarithm 2N0 upon N0 is equal to mu Td. So finally Td is equal to natural logarithm 2 upon mu, which is equal to 0.693 upon mu. Differences lie in microorganisms with respect to their growth and production of products. Therefore, to get the desired product, microorganisms are grown in batch, fed batch or continuous fermentations. Batch fermentation is the second one. Batch fermentation is a closed culture system containing an initial amount of nutrients and involves number of biochemical processes. In batch cultures, the cell properties such as size of cells, nutrients, metabolic function vary considerably during the various growth phases. You can see in the growth profile of figure 2 in the batch culture. The curve is sigmoidal in shape and the various growth phases are shown. The first is the lag phase. The lag phase is considered as adaptation period for the cells to their new environment with no immediate increase in cell number. Commercially, it is beneficial to reduce lag phase length by using a suitable inoculum. Next feature, synthesis of new enzymes ATP cofactor ribosomes, and it also results in slight increase in cell mass and volume. It can be prolonged by poor quality inoculum in terms of volume condition, age or poor medium. This is followed by a exponential phase. In this phase, the cells multiply rapidly, that is exponentially, as well as are well adjusted to their new environment. There is a balanced growth and the growth is at maximum specific growth rate and is independent of nutrient concentration. After the exponential phase is the stationary phase. In this phase, the nutrients get exhausted, that is the substrate concentration is equal to almost 0. Accumulation of undesired secondary metabolic products occurs and the growth rate becomes equal to death rate, that is there is no net growth. The last phase is the decline phase, which is the final stage of cell cultivation. Number of cells decline exponentially due to lysis and the death rate follows the first order kinetics, which is given by dN upon dt is equal to minus kd upon n, where kd is the death rate constant. Upon integration, it leads to n is equal to ns e to the power of minus k dt, where ns is the cell concentration at the end of the stationary phase, Kd is the first order death rate constant. Thus, in batch cultures, the cell properties such as size of cells, internal nutrients, metabolic function vary considerably during the various growth phases. Monod equation growth rate is a hyperbolic function of the concentration of the growth limiting nutrient. The equation is mu is equal to mu m s upon Ks plus S, where mu m is maximum specific growth rate time inverse, S is concentration of the limiting substrate milligrams per liter, Ks is half saturation constant, milligrams per liter is the unit. Ks is the saturation constant at which the specific growth rate is half of the maximum specific growth rate. Monod equation is expressed in terms of cell number or cell biomass as dx upon dt is equal to mu x, we already know that. So, substituting the value of mu in this equation, we get dx upon dt is equal to mu m s x upon Ks plus S. So, Monod equation has two limiting cases. First is high substrate concentration. If the substrate concentration is very high as compared to Ks, so Ks can be neglected from the denominator and then S gets cancelled, and finally the equation becomes dx upon dt is equal to mu m x. So, under these conditions growth occurs at maximum growth rate. This is zero order region with mu is equal to mu m. Second case is of low substrate concentration, where the substrate concentration is much less than the Ks. So, substituting the value dx is equal to dt is equal to mu m s x upon Ks and neglecting the S from the denominator being very small. This type of growth is typically found in batch flow systems at the end of the growth curve as the substrate is nearly consumed. This is first order region with mu is equal to mu m s x upon Ks. The Monod equation can also be expressed as a function of substrate utilization, given that growth is related to substrate utilization by a constant called cell yield. Gives ds upon dt is equal to minus 1 upon y mu m s x upon Ks plus S. This we have obtained by substituting the value of dx upon dt. Thus, y, that is the biomass yield, is equal to the biomass produced in grams upon the substrate consumed. Now, coming to the advantages of batch culture systems. Batch culture systems results in reduced risk of contamination or cell mutation as the growth period is short. There is lower capital investment, production of wide varying product or biological systems can occur, and it results in high conversion rate of raw materials. Besides having the advantages, there are certain disadvantages of batch culture systems, which are as lower productivity levels related to more time consumption, increased focus on instrumentation, requirement of several subculture levels, high costs for labor or process control, more susceptible to pathogenic microorganisms or toxins. We should also know about the applications of batch cultures. So, batch cultures are employed where the products involve low risk of contamination or mutation of microbes. It is used where the production of small amounts of product is required, employing proper product separation in batch or semi-continuous processes. So, the batch growth kinetics are as biomass yield Yx over S is equal to minus delta x upon delta s, product yield y P over S is equal to delta P upon delta S, growth yield based on consumption of oxygen is y x over oxygen is equal to delta x upon delta oxygen. Next is the fed batch fermentation. A fed batch is a batch process which is always at a quasi steady state, as it is based on the non-toxic level feeding of a growth limiting substrate to culture without removing the fermentation broth. It is designed to accommodate the increasing volumes with accelerated cell growth resulting in high cell density. Consider a batch culture in which growth is limited by the concentration of one substrate. The biomass at any point in time will be described by the equation xt is equal to x0 plus y bracket SR minus S bracket closed, where xt is the biomass concentration after time t hours, x0 is the inoculum concentration, SR is original substrate concentration and S is residual substrate concentration. The final biomass concentration produced when S approaches 0 may be described as x maximum, and x is very small as compared to S x maximum, and x0 is very small compared to x maximum. So, ignoring x naught, equation is reduced to x maximum is equal to YSR. Advantages of fed batch systems: high cell yield and it can be operated almost at stationary state. Disadvantages: lower productivity levels due to consumption of time in preparation of fresh run in reactor and high costs for labor or process control. Applications of fed batch: fed batch culture is ideal where high concentration of substrate inhibits microbial growth. Production of intracellular metabolites in maximum amounts. Increased biomass production if desired product is intracellular. Example: two-stage production of penicillin, which is a secondary metabolite. In idiophase, a production phase of penicillin, the biomass is maintained at low levels by feeding phenylacetic acid, a precursor of penicillin, at levels below toxicity. Now coming to the continuous fermentation. Continuous culture is an open process wherein exponential growth can be extended by the addition of fresh medium containing a limiting substrate. Fresh medium displaces an equal volume of spent medium along with the biomass, thus a steady state is reached. In continuous fermentation, the flow of medium is related to the volume of the vessel by the dilution rate D as follows: D is equal to F upon V, where F is the flow rate per hour and V is the volume in liters. The net change in cell concentration over time is expressed as dx upon dt is equal to growth minus output, or dx upon dt is equal to, now since growth is mu x minus output dx. Under steady conditions, the cell concentration remains constant, therefore dx upon dt is equal to 0. So, it implies mu x is equal to dx, that is at steady state mu is equal to d. Thus, under steady state conditions, the specific growth rate is controlled by the dilution rate. Substituting the value of mu maximum S upon Ks plus S in above equation, we get dx upon dt is equal to x whole bracket mu maximum S minus d upon Ks plus x. The net change in the residual growth limiting substrate concentration is given as ds upon dt is equal to input of substrate minus output of substrate minus consumption by cells. So, ds upon dt is equal to dsr minus ds minus mu m x upon y bracket S upon Ks plus S. Now, at steady state, both ds upon dt and dx upon dt equals 0. So, X at steady state is given by Y bracket SR minus S, and substrate concentration at steady state is equal to Ksd upon mu maximum minus D. Thus, we can very well see that D controls mu. If the dilution rate is increased above mu maximum, there is complete washout of the cells and the cells do not get sufficient time to double. The stage just below this situation is called as critical dilution rate, D critical. Homogeneously mixed bioreactor can be of two types in continuous fermentations. Chemostat. Chemostat is a self-balancing culture system where the growth rate of the culture is controlled by its chemical environment, that is the availability of one limiting component in the medium. Turbidostat. It is another type of continuous culture where the concentration of cells and hence the turbidity in the culture is kept constant by controlling the flow of medium. Advantages of continuous culture: accurate information regarding kinetic constants, maintenance energy and growth yields, regulation of growth rates for extended periods by varying the dilution rates, enhances selectivity for thermophiles, osmotolerant or mutant organisms, results in higher productivity per unit volume. Disadvantages of continuous culture include control of some non-growth associated products is not easy, washout phenomena caused by growth on walls and hence cell accumulation results in unsteady state, loss of original product strain over time if a faster growing one overtakes it. Difficult to maintain filamentous organisms due to viscosity and heterogeneous nature of broth. Elongated growth periods increase the risk of contamination. So, we read about the various types of fermentations. Now coming to the microbial products. The microbial products can also be classified into three main categories: growth associated products, non-growth associated products and the mixed growth associated products. Growth associated products are those which are produced along with the microbial growth. Specific product formation rate is thus proportional to specific growth rate mu. The rate expression for product formation in growth associated production is given as Qp is equal to 1 upon x dP by dt, which is equal to product yield, that is Yp over x into mu, where Qp is product formation rate per hour. Production of a constitutive enzyme is an example of growth associated product. Non-growth associated products means the products are produced during stationary phase. Specific product formation rate is constant, that is Qp is equal to beta. Secondary metabolite production, as most antibiotics, example penicillin, are the examples of non-growth associated products. Mixed growth associated product. The products which are produced during deceleration and stationary phases. The specific product formation rate is given by Liu-Deking Pirate equation, which is given as Qp is equal to alpha mu plus beta. Alpha is equal to 0 signifies that the product is completely non-growth associated, while beta is equal to 0 signifies that it is completely growth associated. Examples include secondary metabolites, production of lactic acid and xanthan gum. So, figure 4 shows the profiles of the microbial products. Criteria of bioreactor design. A good bioreactor design should provide improved productivity, validation of desired parameters in a cost-effective manner for achieving consistent and higher quality products. The criteria for bioreactor design is as follows: microbiological and biochemical characteristics, hydrodynamic characteristics of the medium in motion and other forces acting, mass and heat characteristics, kinetics of cell growth and product formation, genetic stability, design related to sterilization, control of bioreactor conditions, design of downstream product separation, capital and operating costs, and finally the scale up. Principal types of bioreactor or the fermenter are batch fermenter, continuous stirred tank fermenter CSTR, tubular fermenter, fluidized bed fermenter. Oxygen transfer rate in microbial processes. In aerobic bioprocesses, oxygen being sparingly soluble is supplied continuously in broths. The gas liquid mass transfer in a bioprocess is strongly influenced by the hydrodynamic conditions in the bioreactors, physiochemical properties of the culture, geometrical properties or the parameters of the bioreactor, and the presence of oxygen consuming cells. So, the figure 6 shows the transport of oxygen from air bubbles to the cells and the various resistances offered for oxygen transferred from gas bubble to cell. The two film theory proposed by Whitman on gas liquid mass transfer in 1923 describes the flux through each film as the product of the driving force by the mass transfer coefficient. Thus, NAG is equal to Kg bracket Pg minus Pi is equal to KL bracket Ci minus Cl, where Kg and Kl are the local mass transfer coefficients, Pg is the oxygen partial pressure in the gas bubble, and Cl the dissolved oxygen concentration in the bulk liquid. Index I refers to values at gas liquid interface. Since it is not easy to directly measure the interfacial concentrations, the overall mass transfer coefficient can be rewritten as NaL is equal to Kg bracket Pg minus P asterisk is equal to Kl bracket C asterisk minus Cl, where P asterisk is the oxygen pressure in equilibrium with liquid phase, C asterisk is the oxygen saturation concentration in the bulk liquid in equilibrium to the bulk gas phase, and Kg and Kl are the overall mass transfer coefficients. Combining equations 21 and 22, the following relationship is obtained, that is 1 upon capital Kl is equal to 1 upon H Kg plus 1 upon Kl. Overall mass transfer coefficient is equal to the local coefficient capital Kl is equal to Kl, as the greatest resistance for mass transfer is on the liquid side of the interface, hence gas phase resistance can be neglected. The oxygen mass transfer rate per unit of reactor volume Na is given as the product of overall flux and the gas liquid interfacial area per unit of liquid volume A, that is Na is equal to A into NaL, which is equal to Kla bracket C asterisk minus Cl. Since Kl and A cannot be measured separately, the product Kla is measured and is called as volumetric mass transfer coefficient, which characterizes the transport from gas to liquid. Maximum oxygen transfer rate OTR max. At steady state, oxygen transfer rate from bubbles equals the oxygen consumption rate by the cells. Therefore, Kla C asterisk minus Cl, which is the oxygen transfer rate, this equals the oxygen consumption, that is Q0x, where Q0 is specific oxygen uptake rate. When Cl is equal to 0, the bioreactor can withstand maximum biomass concentration. So, X max is equal to KLA C asterisk upon Q0. KLA critical is equal to Q0 X upon C asterisk minus C critical. Generally, the critical oxygen concentration is 5 to 20% of the oxygen concentration values in cultures. In Newtonian suspensions such as of yeast and bacterial fermentations, the critical oxygen concentration is constant and is not affected by fermentation conditions. However, in non-Newtonian suspensions containing filamentous microorganisms, the critical oxygen demand is found to be dependent on fermentation conditions. So, we read about the volumetric mass transfer coefficient, that is KLA. Now, we should know that what are the factors which affect the volumetric mass transfer coefficient. So, these are number 1, bubble size. Small bubbles have high interfacial area and hence result in increased KLA. Second, gas hold up. It is the volume fraction of the gas held up in the total volume comprising the liquid and the held up gas together. It is equal to Vg upon Vg plus Vl, which is equal to Vg upon V, where Vg is volume of gas bubbles in reactor and Vl is volume of liquid and V is the total volume, that is of the gas bubbles in the reactor and the liquid. So, higher values indicate higher amount of gas held up in the system. Smaller bubbles stay for longer times in the liquid and result in higher epsilon values and higher mass transfer rates. Smaller bubbles whose diameter is less than 1 mm create nuisance in fermenters. Third, gas velocity. The superficial gas velocity, that is Ug, is the linear velocity of gas obtained on basis of volumetric flow rate of the gas per cross sectional area of bioreactor. KLA is equal to 2 into 10 power of minus 3 bracket P upon V to the power 0.7 into Ug to the power 0.2. Mass transfer rates increases with Ug as if gas flow rate is very high and the stirrer speed is low, the gas does not get dispersed properly. It rises up and results in impeller flooding. So, flow rate is either reduced or agitation speed is increased to increase KLA. If flow rate is too low compared to agitator speed, then gas bubbles rise, simply recirculate. This increases gas hold up but mass transfer coefficient and hence the mass transfer rate reduces considerably. Fourth, types of sparger. Not much information is known on the effect of spargers on mass transfer. Fifth, type of agitator. Type of agitator and agitator design for effective mixing shows great effect on mass transfer rates. Sixth, power input to agitator. The effect of power input on interfacial area is given by the equation you can see, where rho L is the density of liquid broth, sigma L is the surface tension and mu T and ut is terminal velocity. As the interfacial area varies as 0.4 power of the power input per unit volume P upon V. The power input is also related to agitator speed through the power number Np. Np is equal to P upon rho n cube di to the power of 5 or P is equal to Np rho n cube di to the power of 5, where di is the bubble diameter. The dependence of power number on the agitator speed varies based on the type of flow, as power is proportional to n square for laminar regime and power is proportional to n cube for turbulent regime. Seventh, temperature. The temperature has two effects on mass transfer. It increases the diffusivity of the gas into the liquid, it increases the value of KLa. However, increase in the temperature decreases the solubility of gas and hence reduces C asterisk oxygen. So, the net oxygen concentration reduce and thereby it reduces mass transfer. In the range of 10 to 40 degrees centigrade, temperature rise increases the mass transfer, but temperatures greater than 40 degrees centigrade, the mass transfer decreases. 8th, pressure. Pressure affects the mass transfer by increasing the solubility of the gas in the liquid phase, which is given by the Henry's law. So, partial pressure of oxygen is equal to H into C concentration of oxygen. The partial pressure and total pressure of the system are related by partial pressure of oxygen is equal to total pressure Pt into YO2, that is the mole fraction of oxygen. Thus, a total pressure Pt increases, partial pressure of oxygen increases and hence the concentration of oxygen increases, which in turn will increase the driving force, that is C asterisk minus Cl. 9th, anti-foaming agents. Most of the culture broths contain proteins which causes foaming. Use of silicon based anti-foaming agents affects the surface chemistry of bubbles by reducing surface tension. This reduces coalescence of smaller bubbles into larger bubbles, thereby increasing A, that is the interfacial area. However, these surface active agents reduce the motility of gas liquid interface and reduce mass transfer coefficient. Thus, the increase in interfacial area A is countered by reduction of KL, which being larger reduces the overall KLa. 10th, existence of cells. Oxygen transfer in culture broths is greatly influenced by the presence of cells by two ways. First, physical influence. Cells interfere in the breakup and formation of the gas bubbles by influencing their surface properties. These get absorbed on the gas liquid interface, decreasing the mass transfer coefficient. Cells do not allow smaller bubbles to coalesce into bigger bubbles. Hence, the increase in interfacial area is maintained and this in turn results in overall mass transfer. Second, quantitative influence. In quantitative influence, the cells absorb oxygen during the process, which increases the driving force and hence oxygen transfer. The influence of cells in enhancing the mass transfer depends on type of cells, morphology of cells and concentration of cells. Now coming to the optimization of nutritional and physical conditions in bioreactor, the objective of process optimization is in maintaining optimum and homogeneous reaction conditions to minimize microbial stress and in enhancing volumetric productivity using several nutritional example, suitable carbon and energy sources, nitrogen sources, micro elements, inducers, repressors and environmental parameters, temperature, pH, dissolved oxygen, pressure, agitation. Coming to the scale up now, design of a production scale system is based on the performance of a model system characteristics as thermodynamics, scale independent, kinetics, scale independent, transport phenomena like KLa, scale independent. One of the fundamental problems is incomplete mixing on scale up, concentration gradients, cell growth on walls, etc. Similarity between model and prototype systems. For similarity in two mixing systems, it is ideally important to achieve first geometric similarities. Both parameters as the shape and linear dimensions should be related by a constant factor as given like d upon t of one vessel is equal to d upon t of the other, which has to be upgraded. Similarly, in terms of height, h upon t of 1 is equal to h upon t, which has to be upgraded. Second, kinematic similarity. similar flow patterns with a constant ratio of velocities at same points. Dynamic similarity, all forces at same points in two geometrically similar systems should have a constant ratio, that is P naught upon rho n cube d5 of the lower should be equal to P naught rho n cube d5 of the other, which is to be scaled up. Coming to common criteria for scale up, first is constant P upon V. This is the most commonly used criteria for scale up. For non-gas systems at constant P upon V is equal to K Ni cube d square. So, keeping the constant P upon V and equating, so N1 cube d1 square is equal to N2 cube d2 square. Thus, N1 upon N2 is equal to d2 upon d1 whole to the power 2 by 3. For gas system at constant P by V, the equation is Pg upon V is equal to Kni to the power of 7 by 2 di to the power of 7 by 2 upon Q to the power of 1 upon 4. Equating the two, we get the equation N1 upon N2 is equal to d2 upon d1 into Q1 upon Q2 to the power of 1 upon 14. Second, constant KLa, this is desirable for biological processes. N1 upon N2 is equal to d2 upon d1 whole to the power 13 upon 21 into Q1 upon Q2 whole to the power 5 upon 42. Third, constant mixing time, in other words indicates constant Reynolds number. So, NRE is equal to constant, T2 is equal to T1 d2 upon d1 whole to the power of 11 upon 18. Fourth, constant impeller tip speed, that is N1 is equal to N2 into d2 upon d1. Downstream processing, it refers to separation and purification processes of fermentation, enzyme reactions into desired products. It accounts for 60% of the total production costs. Point to be considered while developing a downstream processing are nature of material to be processed, location of the target product, whether it is intracellular, extracellular or exists as inclusion bodies. Third is concentration of product. Fourth is relative properties of the products with respect to contaminants. Fifth is sensitivity to high shear rates, organic solvents, pH and temperature. Sixth is desired physical form of the final product, that is lyophilized powder, sterile solution, suspension. Seventh is percentage purity, and the last is the process economics. Operation of downstream processing on basis of properties are filtration, membrane separation, centrifugation are based on size. Centrifugation, sedimentation, flotation are based on density. Membrane separation is based on diffusivity. Extraction, chromatography, adsorption is based on polarity. Extraction, precipitation, crystallization on solubility. Adsorption, membrane separation, electrophoresis on electrostatic charge. Distillation, membrane distillation per evaporation on motility. So, figure 9 shows the flow chart of downstream processing of biological materials, and figure 10 is the flow chart of manufacturing cost in bioprocess industries. In this module, we learnt about the fundamental basics of microbial kinetics, metabolic stoichiometry, the basics of bioreactor engineering with knowledge on design and operation of fermentation processes. Also, it had helped to understand bioengineering skills for the production and purification of biochemical product using integrated biochemical processes. This module is also available at UGC EPG Pathshala website. Thank you.